Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450 Mission to Mars, Lecture 4 on Orbits, Part 3. So in this part of Lecture 4, we're going to talk about changing orbits. If you have a satellite in a given orbit, what do you have to do to move it to a higher or a lower orbit? So to begin with, let's just review some basics of the movement of spacecraft. So imagine two identical spacecraft, and they're both in circular orbits around the Earth. The first satellite, Alpha, is at an altitude of 300 kilometers, and the second one, Beta, is at an altitude of 420 kilometers. So go out to the lecture exercise right now and answer this question: which satellite is moving faster? All right, what did you get on this one? Well, you can calculate the circular orbit velocities for both of them. And what you will find out is that Alpha, the satellite that's at the lower altitude, is moving faster than Beta, which is at the higher altitude. Then the question comes about, imagine those same two satellites, Alpha at an altitude of 300 kilometers, Beta at an altitude of 420 kilometers. Which satellite has the longer period? That is, which one takes more time to go around the Earth? So go out to the lecture exercise and answer that. All right, let's look at some of these results. What did you get on this one? On this one, of course, Beta, which is at the higher altitude, is both moving slower and it has more distance to cover, so it has the longer period. This table shows us these two satellites, Alpha here with an altitude of 300 kilometers, Beta with an altitude of 420, and then I've just thrown in a separate satellite here with an altitude of 620 kilometers to show you. Here's their semi-major axis, but here's the columns that are most important, their circular velocity and their period. So you will notice that Alpha at an altitude of 300 kilometers, its circular orbit velocity is 7,725 meters per second. Up at the higher altitude of 420 kilometers, Beta, its velocity is only 7,657 meters per second. You'll notice their orbital periods over there on the right-hand side. At the lower altitude, Alpha completes an orbit every 90.5 minutes, and Beta completes an orbit every 93 minutes. So that should match what your notions were from the last couple lectures, that the closer a satellite is to the Earth, the faster it's going. And also then, because it's moving faster and its orbit is smaller, it completes an orbit more quickly than a satellite at a higher altitude does. So let's talk about what happens now to orbits of satellites. Orbital elements of a satellite can evolve and they can change over time, and there's a variety of influences that can cause this. Now, the first one we've already seen in the last lecture. I talked about orbital decay. Orbital decay, also known as atmospheric drag, primarily affects satellites in low Earth orbit, typically those that have an altitude of 800 kilometers or less. Above an altitude of about 800 kilometers, atmospheric drag is not much of a problem. It's not really very significant. So if this is a picture with the surface of the Earth down here, and we've got various altitudes over here shown in miles, but I've written them over here in kilometers, you can see up around 10 kilometers, we're in the troposphere. Up at 50 kilometers, we're in the stratosphere. We really get up into space above the Kármán line, which is at an altitude of 100 kilometers or 62 miles. You might remember me mentioning that in a previous lecture, that it's this artificial line that's drawn for contest purposes and other reasons to say that above that line you're in outer space and below that line you're still in the Earth's atmosphere. The thing about the Kármán line is that the Earth's atmosphere doesn't stop there. The Earth's atmosphere continues above that. In fact, aurora, which are the interaction of charged particles from the sun striking the Earth's atmosphere and making it glow, aurora can occur above 100 kilometers in altitude. And then we have the Space Shuttle and the International Space Station, for example, orbiting up there around 400 kilometers or so. Then we have the low Earth orbits up there at those altitudes and a little bit above that. The Space Shuttle and the International Space Station are still orbiting in the tenuous outer layers of the Earth's atmosphere. As evidence of this, the Space Shuttle, when it would orbit, would very often orbit the Earth tail first. That is, they would point the tail of the Space Shuttle in the direction that they were traveling. Now, there were a couple of reasons for this. The primary reason was those main engines that were used to launch the Space Shuttle. Those main engines were used for the first 8 minutes, a little bit more than 8 minutes into the mission. After that, the giant external tank is discarded. Those main engines no longer have any fuel. They shut down, and they're not needed for the rest of the mission. As you're orbiting the Earth, then, since you don't need those engines, it makes sense to point them forward because your most dangerous space debris, the most likely direction that you will encounter space debris, is the direction in which you're moving. So if they oriented the Space Shuttle with the tail forward, any debris would hit those engines, which weren't needed for that particular mission. That meant that when the astronauts would orbit on the night side of the Earth, they would often see the tail of the Space Shuttle glowing eerily. And this tail is because the Space Shuttle is plowing through the outer layers of the Earth's atmosphere at a speed of about almost 7,700 meters per second. And it's plowing through the atmosphere so quickly that it's exciting molecules in the Earth's atmosphere to glow. And this glow is somewhat similar to aurora, slightly different physical process, but in this case, as the Space Shuttle plows through the atmosphere, this collisional excitation with that gas causes that gas to glow. So as I mentioned, orbital decay is worse for low Earth orbits. It's also worse during times of increased solar activity. When the sun has its maximum sunspot activity, we say that the solar activity is increased, those sunspots produce extra ultraviolet light, and that causes the Earth's atmosphere to puff up slightly. And because the Earth's atmosphere puffs up slightly, at any given orbital altitude, the density of the atmosphere increases. And so you will see the decay of satellites increase during increased solar activity. And if you're in orbit around the Earth, in low Earth orbit, you have to boost yourself to compensate for this drag. And that drag compensation requires a change in velocity. And over the course of a year, a typical satellite might have to change its velocity by 25 to 100 meters per second to compensate for this atmospheric drag, this drag that's bringing it down. Okay, so that's a little bit about atmospheric drag. That's one of the things that causes orbits to change. And your option with with atmospheric drag is, in the case of the Space Shuttle or the Space Station, as your orbit falls, you can reboost yourself. Or with many other satellites that don't have thrusters on board, they just accept the loss of orbital altitude, meaning that someday the atmosphere will get thick enough that your satellite will re-enter the Earth's atmosphere. So the question I have for you is this. Atmospheric drag will cause a satellite to slow down, right? As you're plowing through the atmosphere, it's slowing you down. What will this cause its orbit to do? Will it cause its orbit to decrease in altitude and decrease in speed? Decrease in altitude and increase in speed? Increase in altitude and decrease in speed? Or increase in altitude and increase in speed? Or decrease in altitude but maintain the same speed? So what does atmospheric drag do to a satellite? Go out to the lecture exercise and answer this. All right, so what do you think in this case? What's going to happen to the satellite? Well, we've already seen that because of atmospheric drag, the satellite slows down. And we've already seen with the case of the International Space Station that the altitude decreases. That is, ignoring these boost maneuvers where they've boosted the International Space Station, and this maneuver right here where they intentionally decreased the altitude of the space station, you will notice that over the long term, there is a gradual decline in the altitude of the International Space Station because of atmospheric drag. The question then is what happens to the speed of the International Space Station or the shuttle or any satellite as it falls? And that's counterintuitive. What's counterintuitive about it is that as the orbital altitude decreases, the speed increases. And we saw that a minute ago with these satellites, that as your orbital altitude decreases, your speed increases. So the amazing thing about atmospheric drag is that as your space station, as your spacecraft plows through atmospheric drag, it's losing energy, it's slowing down and falling to a lower orbit. But as it falls to a lower orbit, it converts some of that potential energy that it had into kinetic energy, and the satellite actually speeds up. Another really good example of this, if you've ever paid attention to it, is if you've ever been to the mall and you've used one of those giant coin black holes. It looks like a curved surface, and you put your coin in it, and it rolls around on the outside of this curve, and then friction between the coin and the surface is slowing your coin down. And as your coin slows down, it falls deeper and deeper into the well. Well, as it falls deeper and deeper into the well, the coin actually moves faster and faster. And that's because, like a satellite, the friction is causing the coin to slow down and lose energy. As it loses energy, it falls into the well. But as it falls into the well, it converts some of that gravitational potential energy into kinetic energy, and it speeds up. So as satellites decay, as they come down from orbit, it turns out they also move down to orbits that are faster. They speed up. Now, orbital decay is not the only thing that affects a satellite. There are other orbital perturbations as well, as we call them. And one of the most important ones is called nodal regression. It is a tilting of the orbit, or I shouldn't say a change in the tilt. The inclination stays the same, but the orbit wobbles around. Okay? So let's talk about what causes this before we go into the details of what it looks like. It's caused by the fact that the Earth is not perfectly circular. The Earth bulges out at the equator, and it's a little bit narrower around the poles. In fact, the equatorial radius of the Earth, the one that we've been using this whole semester, is 6,378 kilometers. But the polar radius of the Earth is just 6,357 kilometers. You can see that the radius of the Earth is 21 kilometers less around the poles than it is around the equator, which means that the Earth bulges out at the equator. And you can imagine then, I'll come back to this page in a second, that as a satellite orbits the Earth, that bulge is pulling on the satellite. That is, when a satellite is inclined to the Earth's equator, when it is north or south of the equator, that bulge around the equator is pulling down on the satellite. Now, what effect does this have? Well, it turns out it does not change the inclination of the satellite. You would think, looking at this diagram, that force pulling up on the satellite right there would try and flatten the orbit out. But it turns out that satellites, anything that's spinning, doesn't respond like that. We'll see how it responds here in a second. But before we see how it responds, let's try and understand what's going on. So I'm going to watch this video here, bring up this video, and I'm going to turn down the sound on this video, and I'll explain what's going on here. All right, so here's a picture of a satellite orbiting the Earth. So a couple quick things that we have on here. This satellite is in a 400-kilometer circular orbit that's inclined by about 28 degrees with respect to the equator. And over the full length of the video, we're going to watch a total of 5 days worth of orbits of this satellite. So you can see, first of all, the satellite is going around the Earth about every 90 minutes or so. The Earth is taking 24 hours to turn underneath it. So something we've mentioned a few times before is that the Earth is turning underneath the orbit of the satellite. The yellow line that you see here, that yellow line is the Earth's equator. And of course, the red line right there, that's the orbit of the satellite, and the red dot represents the satellite itself. This red arrow right here, that red arrow represents the vernal or spring equinox. And you might remember that that's the origin point in the sky that all of our coordinates are measured from. And it's just some arbitrary direction that astronomers picked in the sky. The place where the satellite crosses the Earth's equator, going from south of the equator to north of the equator, you'll remember that that point right there is called the ascending node of the orbit. It's the node because that's where the orbit intersects the equator, and it's the ascending node because the satellite is going from south of the equator to north of the equator. Now, what you might notice about that ascending node is that it's not sitting still. At the beginning of the video, it was over here on the vernal equinox, and you'll notice that every orbit, it shifts over just a little bit. If it weren't for the fact, if the Earth were a perfectly tiny point down at the center, a perfectly spherical tiny point down at the center, and we didn't have any other bodies like the moon and the sun and the other planets pulling on the orbit of a satellite, the node there would stay still. The node, the orbit would remain in its perfect orientation. It wouldn't shift around at all. But because of the equatorial bulge of the Earth, and that bulge is pulling down on the satellite here and pulling up on the satellite over here, the effect is not that the inclination changes. In fact, the inclination stays the same. It's that the orbit wobbles around. It wobbles very much like a top, and we call this precession. The orbital plane precesses or wobbles. And because this node is moving, and it's moving towards the west, we call it the regression of the nodes. Okay? So this is another change that happens with satellites. If you're a satellite operator, and you're interested in having your satellite pass over certain parts of the Earth at certain times of day, you have to take this nodal regression into account. And as we saw in the last lecture, there are a series of orbits inclined by about 97 degrees with respect to the equator, 97 or 98 degrees, that this nodal regression also matches the rate that the Earth goes around the sun, so that in that case, the orbit regresses, the orbit precesses or twists like this, but at the same rate that the Earth is going around the sun, so that the orbit always maintains the same alignment with respect to the sun. Otherwise, what's going on in this case is the orbit is just shifting. Now, this is a natural part of satellite orbits. For most satellites, it doesn't make any difference at all, especially, for example, if it's a communications satellite or an astronomy satellite or something that isn't really looking down at the surface of the Earth. You don't have to worry so much about the nodal regression. It just happens. So that is a picture of nodal regression and what it is. So now what we want to do is understand why it comes about. Why is it that if the Earth has a bulge here and a bulge here, which is pulling down on the orbit here and up on the orbit here, why doesn't it just flatten the orbit out? Why doesn't it just take the orbit and try and bring it into the Earth's equator? Why instead does the orbit wobble? And the answer to that is how all spinning objects behave. A top is a perfect example. If you think about a spinning top, what happens when it's straight up and down, gravity's pulling down along the top. When you tilt the top over, gravity is now trying to torque it, to curve it. But rather than just knock the top over, how the top responds is it spins around. So I've got a couple videos here that I will play to try and help you understand a little bit about precession and what it looks like. So let me start with this first video, which is a demonstration of precession using a bicycle wheel.
And I've been following this series by Destin on Smarter every day about helicopters and gyroscopic precision.
Oh, well, it does exactly what you'd expect. It's pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum round that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin.
All right, here's another video that shows the same thing.
It has has angular momentum, which physicists like to define with the right-hand rule, as along the axis it's rotating about. Curl your fingers with the direction of the spin, and your thumb points along the angular momentum vector. Angular momentum is just like regular linear momentum. Something that's moving wants to keep moving unless there's a force stopping it, like friction. In the same way, this wheel wants to keep spinning with its angular momentum vector pointing in the same direction, unless there's a torque stopping it, like my hand. When you apply a torque to something, that is a force some distance away from whatever you're going to rotate that thing about, it can make it spin faster or slower, or change the direction it's spinning. Put simply, torque wants to increase angular momentum in the direction of that torque. Watch this. Gravity is applying a force here. Now this is where it gets confusing, because just like angular momentum is defined as not really in the direction that the wheel is spinning, but out of the spinning plane, torque is defined as R cross F, which by the right-hand rule is also in a third direction. So a torque on the wheel like this would increase momentum in that direction. A torque this way, like that due to gravity, would make the angular momentum vector want to rotate that way, and the gyroscope will turn, what we call gyroscopic precession. Now back to the egg. It works similar to the wheel's precession. In fact, the egg precesses. In order for the egg to stand up,
Hi there. If you're watching this video, you're probably already aware of the phenomenon of gyroscopic precession and how you can predict and calculate the effect by using angular momentum vectors. But no matter how good you get at calculating these vectors, and no matter how many times you do those calculations, you might be left feeling that the spinning wheel demo seems totally amazing and weird, or that these vector explanations are completely unintuitive. I sure did. So I made this video to share how I intuitively understand gyroscopic precession. We're going to start out considering satellites in orbit, but don't worry, we'll be back to the bicycle wheels soon enough. If you've played Kerbal Space Program much, this will probably be even easier to understand. So here's a single satellite in a perfectly flat circular orbit. What happens if we push up here and push down here? To be more specific, we're going to push up and down on the satellite as it passes these 2 points. If you forget that the satellite is in motion and just imagine that its orbit is a giant hula hoop, you would expect the orbit to tilt like this, but that's not what actually happens. Let's think about the satellite again. As it passes this point, we push up on the satellite. Pushing up on the satellite doesn't cause it to teleport upwards and then continue moving in the same direction. It just gets sent flying in a different direction. And if you trace out the path that it takes, the orbit is tilted like this. Now keep in mind that the forces we applied on the satellite were equal and opposite, so they combine to form a twisting force around this axis. But we can clearly see that the orbit was tilted around a completely different axis. Now before we continue, make sure you're completely comfortable with this idea. Pushing up on the satellite here causes the orbit to tilt like this. Feel free to pause the video, rewind, or even go ahead and play Kerbal Space Program until you get the idea. Now, let's look at the classic example of a bicycle wheel suspended from a rope. A bicycle wheel is obviously a solid piece of rubber, but I'm going to replace it with individual balls of rubber. It makes no difference to the end result, but it makes it easier to think about. Gravity is pulling down on the wheel here, and the rope is pulling up here. These forces combine to produce a twisting force, called a torque, trying to twist the wheel this way. Now this twisting force is totally equivalent to pushing right on the wheel here, and left on the wheel here. Either way, the twisting action is trying to turn the wheel clockwise. Now, we shift our point of view to look at the wheel from above. Does this scene look familiar now? It looks just like our orbiting satellite, except instead of just one satellite, we've got a whole bunch in the same orbit. But once again, this makes no difference. As the rubber balls get pushed up and down, they get diverted into a new path, rotating like this. Now, of course, I've made some simplifying assumptions here. In reality, the torque is applied via the bearings in the hub of the bicycle wheel, rather than via magic force arrows, and the force is probably spread out around the hub rather than applied at just 2 points. But once again, it turns out that none of this makes any difference to the end result. No matter how you apply torque to a rigid body, the end result only depends on the total torque applied. So I think the model I've shown is as good as any, and I hope it's nice and easy to think about intuitively. So that's it. Please do let me know whether or not this video helped with your understanding, and thanks for watching. See you.
All right, so those are a couple quick explanations for what's going on here. So in other words, as the bulge of the Earth pulls up on the orbit right here and down on the orbit here, the orbit responds not by flattening out, but by wobbling instead. And you saw a couple really nice explanations of that wobble there. It's related to the gyroscopic precession of a wheel, or I really like that last video where he actually used a satellite and showed that what happens if you push up on the satellite is not that the orbit flattens out, it's that the satellite going this way is now going this way, and it tilts the orbit at a right angle to how you apply the force. All right, what are some other perturbations that happen with satellites? We've seen atmospheric drag, slowing it down, bringing it down to a lower orbit. We've now seen nodal regression, the fact that the orbit wobbles over time. There are some other minor effects that you have to account for. Mass cons, which is short for mass concentrations, will speed up and slow your satellite down. If your satellite is flying over the Himalayas, for example, that's a huge mountain range. It has a tremendous amount of mass. All that extra mass concentrated on the surface of the Earth has a little bit of gravity associated with it. It'll actually pull on your satellite and accelerate it, and then your satellite will pass over the Himalayas, and then all that mass will pull backwards on your satellite. And so you can find, or as your satellite is orbiting the Earth, it is constantly speeding up and slowing down because of irregularities on the surface of the Earth, having a little bit of extra or a little bit less than average gravity. The Earth not only spins, but the Earth wobbles, and so that Earth axis wobble can change the location of your satellite in orbit. And then you've got things like the sun, the moon, and Jupiter, and they're constantly pulling on your satellite as well. So even though your satellite might be in a nice, constant, steady orbit, you've got the moon pulling on it, you've got the sun pulling on it, you've even got the effects of Jupiter pulling on it, and all of those are going to cause your orbit to adjust over time. And then finally, another significant one is solar photon pressure. When you're out in the bright sun and the sun is shining on your face, you don't think of those photons of light as actually pushing on you, but they do impart some momentum on you. They do push on you with a slight force. When a spacecraft is in orbit around the Earth, or when a spacecraft is in deep space, that solar photon pressure is actually pushing on the satellite. And in fact, it's significant enough that you can easily detect it on satellites, especially satellites that have one giant solar array on one side and not a balancing solar array on the other side. As the photon pressure pushes on that solar array, it will actually torque and spin the satellite. So the satellite has to use its attitude control system to come back and adjust itself. So solar photon pressure, the pressure of light pushing on your satellite, can be significant, especially if your satellite is asymmetric. It's got to say a solar array on one side and nothing on the other. All right, let's talk now about changing orbits. Imagine that you're in one orbit and you want to change to go to another orbit. Well, to do that, you're going to have to apply some change in speed to your satellite. And we call that change in speed, of course, a delta V. So let's think about the most natural delta V, which is getting your satellite from the surface of the Earth into orbit to begin with. How much delta V does that require? Well, to go from launch to a 300-kilometer circular orbit requires a delta V of at least 9,440 meters per second. There are two things that you need to do. First of all, you need to get into circular orbit, and that circular orbit requires that you're traveling sideways at 7,726 meters per second, right? So that's the first component of the delta V that's needed. The second component of the delta V that's needed is it's going to take some work. Your satellite is pretty heavy. We've got to lift it against the force of the Earth pulling it down. We've got to put some work into it. And you'll remember energy is the ability to do work. So the work required, the change in energy required to get your satellite up to 300 kilometers equates out to a speed of about 1,715 meters per second. So those two combined, the 7,726, the 1,715, result in a total delta V of about 9,440 meters per second. But that's not it. This also assumes that as your rocket is launching, it doesn't encounter any atmospheric drag. And of course, especially early in the launch when the atmosphere is very thick, you will be experiencing atmospheric drag, and you're going to have to put in extra speed just to overcome that atmospheric drag trying to slow you down. For a typical rocket, That probably adds another 1,500 meters per second or so to what's required to get into orbit. So that's an example of the delta V required to get into orbit. You need the circular orbit velocity. You need to put some energy into lifting against the force of gravity. And then you also need to put some energy into counteracting the aerodynamic forces on your rocket. But now imagine that you're in orbit and you would like to go to a higher orbit. And imagine that we launch your satellite into a 300-kilometer circular orbit with the intention of boosting that satellite up to geostationary or geosynchronous orbit. So let's think about that transfer. The best way, the most energy efficient way to transfer from one orbit to another orbit is to do an intermediate elliptical orbit that's called a Hohmann transfer orbit, named for the person who first developed this technique. So let me show you a picture of it, and then we'll come back and talk about more details. Imagine that I'm in a low Earth orbit right here, and I'm in a low Earth circular orbit, and then I want to be in a high Earth circular orbit right here. I need to get from the low orbit to the high orbit. There are many different ways I can do this, but the most energy efficient way is to fire my rocket engine here, to fire my thrusters, to change myself from being in this circular orbit right here to putting myself into an elliptical orbit. And this elliptical orbit has a perigee that's at my original altitude and an apogee that's at the altitude of the new higher orbit. Basically, it's an elliptical orbit that precisely matches my old one to my new orbit right here. Then when I get up here to the top, I'm going to have to fire my engine again to bring myself into this circular orbit. And now we're going to look at all the details of this, but I just wanted you to get an overview of it to begin with. So a Hohmann transfer orbit like this, it's used to increase or decrease orbital altitudes. And what it assumes to begin with is that both orbits are in the same plane. It doesn't include any maneuver to change the orbital inclination. We'll see what that requires in an example later on in this lecture. So for right now, we're just going to assume that they're both in the same plane. And as I showed you, it intersects this elliptical orbit that you're going to put yourself into, intersects your orbit at perigee and your orbit at apogee. 2 burns are required for this, one at perigee and one at apogee, and it is by far the most common orbital maneuver that's out there. All right, so let's talk specifically about this new orbit you're going to put yourself into. So the first thing is, how high is it here and how high is it here? Well, again, from the center of the Earth right here, to be up in geostationary or geosynchronous orbit, that requires a height of 35,786 kilometers above the Earth, or a distance from the center of the Earth of 42,164 kilometers. You might remember calculating that in the last lecture. So to be up here, geostationary orbit, that's just the distance from the center of the Earth. Down here at perigee, we said that you were at an orbital height of 300 kilometers, which means the distance from the center of the Earth is 6,678 kilometers, assuming the radius of the Earth that we always assume in spaceflight, which is 6,378. So the question I want you to answer in a lecture exercise, if your perigee distance here is 6,678, and your apogee distance right here is 42,164, what's the semi-major axis of this new orbit? So go out to the lecture exercise and answer this question. What is the semi-major axis of the Hohmann transfer orbit that gets you from 300 kilometers above the Earth up to 42,164 kilometers from the center of the Earth? All right, I'll leave this slide up while you go out there and answer that question. So what is the semi-major axis? All right, what did you come up with for this one? Let's take a look. So we said that at perigee right here, the altitude from, or I should say the distance from the center of the Earth was 6,678 kilometers. And at apogee up here, the distance was 42,164 kilometers. So you can add those two numbers together to get the major axis of the ellipse. So the major axis of the ellipse is just the distance at apogee plus the distance at perigee. And the semi-major axis is just half of that. So we just add 42,164 plus 6678 and divide by 2. And that gives us a semi-major axis of 24,421 kilometers. So that is the semi-major axis of your new Hohmann transfer orbit. That's going to get you from your 300-kilometer orbit up to your geostationary orbit. Now, to put some of the things that we've learned into practice, what's the orbital eccentricity of this new orbit? You've now got the semi-major axis, so that's the first thing. To understand the shape of the orbit, you need to know its eccentricity. And you might remember that I gave you a formula earlier in the semester, or earlier in lecture 4, about how to calculate the eccentricity of an orbit given the minimum and maximum distances. You may need to go back and look at your notes to remember that formula. So calculate the eccentricity of this Hohmann transfer orbit. All right, what did you get for this one? Well, you might remember that that formula says that the eccentricity is the distance at apogee minus the distance at perigee divided by the distance at apogee plus the distance at perigee. In other words, take the apogee distance minus the perigee distance and divide it by the apogee distance plus the perigee distance. You plug all the numbers into your calculator, you come out with an eccentricity of 0.7266. So that's the eccentricity of your new orbit. 0.7266, that's a pretty elliptical orbit. As you can see, one focus of this new orbit is here at the Earth, and the other focus out here is empty, but that's a pretty elliptical orbit. Well, now that we know the eccentricity, in fact, mostly calculating the eccentricity was just to do it so that we know what the number is, we don't really need it for this next question, which is what's the orbital period in hours? So how long does it take my satellite to orbit the Earth in this new Hohmann transfer orbit? So go ahead and use Kepler's third law as modified by Newton to calculate the orbital period in hours. Now remember, that equation will give you an answer in seconds, so you will need to modify it. You will need to convert it to get it in hours. What's the orbital period in hours? All right, welcome back. So let's talk about how to do this one. Now, this one's fairly straightforward. It's just an application of Kepler's law as modified by Newton, but there's a fair bit of numbers that you have to punch into the calculator, so let's take a look at it. You will remember that the period squared is equal to 4 pi squared times the semi-major axis cubed over g times m. Okay, so that was Kepler's law as modified by Newton. The period is measured in seconds, r has to be measured in meters, and the mass has to be measured in kilograms. So now we know our answers here. 4 pi squared are a constant. The semi-major axis, well, we calculated that before, and that turned out to be 24,412 kilometers, right? That was this is the first one that we did here. So that's 24,421. So it's 24,421 times 10 to the 7th meters, right? Because that was in kilometers. So 24,421 kilometers converted to meters is 2.4421 times 10 to the 7th meters. Don't forget to cube it right there. We divide by g, 6.674 times 10 to the minus 11th, and we divide by the mass of the Earth, 5.972 times 10 to the 24 kilograms. Plugging all those numbers into our calculator, we come up with the period squared being 1.443 times 10 to the 9th seconds squared. We take the square root of that, and we get a period of 37,981 seconds, which is about 633 minutes, or 10.55 hours. And what that means is in this Hohmann orbit, to go from perigee all the way back around to perigee again is about 10.5 hours, which means to get from perigee up to apogee will be half of that, and to get from apogee back down to perigee will be another half. So when you fire your engine here, it will take about 5.25 hours to climb up to geostationary altitude right there. in 5¼ hours. That's not a lot of time at all, but that's how long that half of the orbit will take. If you didn't fire your engine here, if you could just continued on this elliptical orbit, well, you would come back down and you would be in this elliptical orbit, and it would take you would orbit the Earth every 10½ hours. Okay, so that's the orbital period. Now the question is, and this is the interesting one that we need to figure out, is how much delta V do I need here, and how much delta V do I need here to get out of this orbit into the Hohmann transfer orbit, and then to get out of the Hohmann transfer orbit into this circular orbit? Because as you're going to find out, we need to fire our engine here to speed up, and then we need to fire our engine here to speed up so that we can be in this higher circular orbit. So let's look very quickly at what are my circular orbit velocities down here and what's my circular orbit velocity up here. In my low orbit down here, which you'll remember was 300 kilometers above the surface, or 6,678 kilometers from the center of the Earth, we can use our circular orbit velocity equation to say that I'm traveling at 7,726 meters per second. So that's how fast I'm traveling down here. In this final circular orbit up here, how fast do I need to be traveling? Well, the answer is 3,075 meters per second, right? And that's just taking the orbital altitude of geostationary orbit, which is 42,164 kilometers, plugging it into the circular orbit velocity equation, and we get 3,075 meters per second. Now, you might say to yourself, now, wait a second, that is slower than this. So when I climb from this orbit up to that orbit, won't I be going too fast? And the answer is no. Remember Kepler's second law. Kepler's second law says that when you're in an elliptical orbit like this, you're traveling faster when you're closer to the bottom, and you're traveling slower when you're up at the top up here. As the satellite climbs up out of the Earth's gravity, it's going to convert some of its kinetic energy into potential energy, gravitational potential energy, and that's going to slow it down until when it finally reaches this high orbit up here, it's traveling slower than it was before. So it looks like you've got more than enough speed down here. It turns out you don't. In fact, something we haven't answered yet, if I'm in an elliptical orbit like this, we saw from Kepler's second law of planetary motion that angular momentum is conserved, that I'm moving faster down here and I'm moving slower up here. And we hinted that the conservation of areas, the fact that the area is conserved, tells you how much slower you're moving or how much faster you're moving. But now let's actually find an equation that does that. And the equation that does that is called the Vis-Viva equation. And the Vis-Viva equation describes how fast you're moving at any moment in time in an elliptical orbit. And here's the equation. At any moment in time, your velocity squared is equal to g times m times this quantity, 2 over your current distance from the orbiting body minus 1 over the semi-major axis. Right? It's just a little bit of algebra, and so we just need to plug numbers into that. And so let's do this for our Hohmann transfer orbit. Let's calculate in our Hohmann transfer orbit how fast we're moving down here and how fast we're moving up here. So let's calculate what that is. So let's do it. So when I am at perigee and apogee, so the semi-major axis for my Hohmann transfer orbit is 24,421 kilometers. When I'm at perigee down here at the bottom, when I'm closest to the Earth, I'm 6,678 kilometers from the center of the Earth. So now let's plug our numbers in. V squared is equal to gm times 2 over the distance minus 1 over a. Now I have to be careful here because both of these are in kilometers, and in my equation to get the velocity they need to be in meters. So I need to convert both of those to meters. I take 2 over the perigee distance minus 1 over the semi-major axis, and that gives me the velocity squared, and I take the square root of that. Sorry, I should have put an extra step in there to show you the square root. I take the square root, and what I find out is down here at the bottom where I'm moving fastest, when I'm at perigee, I'm moving at 10,151 meters per second. Up here at the top of the orbit, how fast am I moving? Well, now at the top of the orbit, my semi-major axis is 2,421 kilometers. My distance from the Earth is 42,164. That's the altitude of geostationary orbit. And now I plug it into the vis viva equation. It's g times m times 2 over the perigee, sorry, in this case I should have changed that. That's the apogee distance, minus 1 over a, and the speed up here is 1,608 meters per second. So to try and simplify this, let me just put the arrows in there. If you're in that transfer ellipse that goes from perigee to apogee, the Hohmann transfer ellipse here, down at the bottom, when you're 300 kilometers above the surface of the Earth, you're traveling 10,151 meters per second. And then as you climb up to apogee up here and you get higher and higher and get slower and slower, you're at 1,608 meters per second when you get up to the top up there. And then, of course, as you fall back down, you'll speed up. And then as you continue in this transfer orbit, just like Kepler's second law says, you'll be traveling faster when you're closer to the Earth and slower when you're further from the Earth. But now let's compare these two numbers to our circular orbit velocities. Because here's the thing. To go from my circular orbit, which had a speed of 7,726 meters per second, to get into this elliptical transfer orbit, I've got to speed up. Because at the bottom of this elliptical transfer orbit, I would be traveling at 10,151 meters per second. When I'm in a circular orbit, I'm only traveling at 7,726 meters per second. So I need to fire my engine to speed myself up. And that's the direction that I need to fire my engine. I need to do it very quickly, and I need to speed myself up. How much speed do I need to gain? Well, the delta V is just the speed at perigee of the orbit that I want to be in minus the speed that I currently have. So I want to be traveling 10,151 meters per second. I'm actually traveling at 7,726 meters per second. So if I fire my engine and I gain 2,425 meters per second, it will push me from being in this circular orbit to being into this Hohmann transfer orbit right there. So now I'm in this Hohmann transfer orbit. Now I wait 5.25 hours, and I get up here to the very top. And now that I'm at the very top of the orbit, how fast am I traveling? Well, we just saw that now at the top of the orbit, I'm traveling 1,608 meters per second. But interestingly, that's not fast enough to be in a circular orbit up there. To be in a circular orbit up there, you'll remember using the circular orbit velocity, I had to be traveling at 3,075 meters per second. So now I have to fire my engine a second time, and I have to speed up again. If I don't speed up, I will just fall back down on this elliptical transfer orbit. To get into this circular orbit, I now need to be traveling 3,075 meters per second. I'm actually traveling 1,608, so I need to gain a total of 1,467 meters per second. The total to change from here to here requires a total change. This change to get into the transfer orbit required a delta V of 2,425. To get into the circular orbit later required a change of 1,467. So the total delta V that's required is 3,892. Now, I want you to look at that number for a second because that's important. That's a huge speed change. To give you an idea of how much of a speed change that is, look at your circular orbit velocity when you were in low Earth orbit. It was 7,726 meters per second. It took a full-sized rocket, multiple stages, to get you traveling at 7,726 meters per second. The delta V that's required to go from this low orbit up to geostationary orbit is more than half as much. That is, it takes half as much speed change that it took to get you into orbit to get you up to that higher orbit to begin with. Another way to put it in perspective is let's look at an actual space vehicle. When it was on orbit, you will remember from the homework assignment that the space shuttle used these two orbital maneuvering systems. So here are the three main engines on the space shuttle right here. And the space shuttle also had small thrusters on board that could be used for very small changes. And then they had these two OMS pods, this pod that sits out here and this pod that sits out here. They're called the OMS system, OMS, the orbital maneuvering system. And it consisted of these small thrusters, and it also consisted of these larger thrusters that were used for major orbit changes. Well, once the space shuttle was on orbit, once they had discarded the external tank and these main engines are useless now because they're not needed anymore, these OMS pods would do all the orbit changing. And the space shuttle carried enough fuel to produce a total delta V of about 300 meters per second. To have taken the space shuttle from a low Earth orbit up to geostationary orbit would have required a delta V of about 3,892 meters per second. So the space shuttle, when it got into orbit, did not have sufficient maneuvering fuel to get itself up to even geostationary orbit, let alone, you'll remember, and you could calculate what the delta V would be from this low orbit to get you to escape velocity, and the space shuttle could not do that either, did not carry enough fuel to do that. So here's what the inside of the space shuttle looked like. What we're interested right now are these OMS pods that were up here on the back end of the space shuttle. So those thrusters used a type of fuel, we'll talk more about this later in the semester, called hypergolic fuel. This is where you mix the oxidizer and the fuel together and they automatically combust. If you think about mixing hydrogen and oxygen or kerosene and oxygen together as a fuel, they require some kind of igniter. You need a match, a spark to light that ignition. The problem is that igniter is a point of failure. If that igniter doesn't ignite, your engine won't ignite and you'll be stuck. You'll be in a lot of trouble. Hypergolic fuels have the advantage that if you take the fuel and the oxidizer and you mix them together, they automatically combust. So let's talk a little bit about getting satellites from low Earth orbit into geostationary orbit up there. You have to do two things typically. You not only have to put yourself into a Hohmann transfer orbit to get you up to this higher orbit, but you also have to often change planes. See, when you launch from the surface of the Earth, the inclination of your orbit is typically not 0 degrees. If you're lucky enough to launch on the equator, you can launch yourself into a 0 degree inclination orbit. But if you're trying to get to a geostationary orbit with 0 degrees inclination, and your launch inclination was something larger than that, you will also need to expend fuel to change your inclination. And typically what a satellite operator will do is that they will launch their satellite into what's called a geostationary transfer orbit. That's an orbit that has a low point just above the surface of the Earth and a high point that's very far above the surface of the Earth, typically at geostationary orbit altitude. The problem is this initial orbit is inclined to the geostationary orbit, which is above the equator. Well, as your satellite is orbiting the Earth, at some point in time when your satellite passes over the Earth's equator, you will fire your thrusters and you will do a plane change maneuver. And that plane change maneuver, that's what they talk about here, is where you change the inclination of your orbit. You go from the inclined orbit to a 0 degree orbit. And then once you get up here to the top of your Hohmann transfer orbit, that's when you fire your thrusters again to circularize your orbit and put yourself in that circular geostationary orbit. Now, you don't necessarily have to use a Hohmann orbit. If you're in a hurry to get up to geostationary orbit, you can actually put yourself into a super geostationary orbit. That is a transfer orbit that goes well above geostationary orbit. And then the time that it takes you to get from low Earth orbit up to geostationary orbit is less. Now you might wonder, why would you want to do this? Because, 5 hours, it's not that long to wait. If your satellite's going to be in orbit for 15 or 20 years, it seems like 5 hours is a short time to wait. This is commonly used when you're dealing with an upper stage on the rocket. You've launched and you've got the upper stage on the rocket, and you want to use up that upper stage as quickly as possible. In part, possibly because that upper stage isn't qualified for operating in space for long periods of time. It's probably running off batteries. Those batteries could run down, for example. Starting and restarting those engines, the system may not be qualified for that. So you may want to use up that rocket stage immediately and get as much energy out of it as you can and put yourself into this much higher transfer orbit like this. And then when you get up to geostationary orbit here, fire your engines to change your orbit right there. So that's a possibility. That's a fast transfer orbit. And as I said, they're typically used when upper stages, when you've got excess fuel that's available in an upper stage and you're just trying to burn up and use up that upper stage as quickly as possible. Another time you might want to use these, and this becomes important with Mars, is if you're trying to get from Earth orbit around the sun to Mars orbit around the sun. Turns out the Hohmann transfer orbit is not only the most energy efficient, takes the least energy to do it, but it turns out it's also the longest way to get there. It takes the longest amount of time. And if you've got human beings on board for a mission to Mars, we will likely do a fast transfer orbit to get to Mars to get the astronauts there faster. It's going to take more fuel and it's going to take more energy, but it's worth it because otherwise the transfer orbit, which we'll calculate later on, that transfer orbit could be quite slow for getting to Mars. Now, we talked earlier in the semester, in one of the earlier lectures, about changing the direction of a satellite and how much energy, how much fuel that requires. Plane change, orbital plane change maneuvers, where you're in one orbit and need to change to another orbit, they're very expensive in terms of fuel as well. The simple plane change formula says, look, if I'm in one orbit and I want to change to another orbit and they're separated by some angle, theta here, the delta V that's required is 2 times the circular orbit velocity times the sine of the angle over 2. So let me give you an example. Let's imagine that I want to tilt my orbit by 30 degrees. I'm in an orbit that's inclined by 30 degrees and I want to change that inclination to 0 degrees. And I'm in an orbit where I'm orbiting the Earth at 7,000 meters per second. How much delta V does that require? Well, it's 2 times 7,000 times the sine of 30 divided by 2, which is 3,623 meters per second. So now suddenly, I hope you're getting the whole point of this is to show you that once you are in orbit, it is very, very difficult to change your orbit. It is very energy intensive. To get from low Earth orbit to geostationary orbit requires half the delta V that it took you to get to orbit in the first place. And here you'll notice that to change the inclination of your orbit by just 30 degrees, again, requires about half the energy that it took you to get into that orbit in the first place. Once you are in orbit, changing orbits is incredibly energy dependent. It consumes a tremendous amount of fuel and energy. I'm going to give you an example that was quite common in the media in the early 2000s, and it's the Space Shuttle Columbia accident. So on January the 16th of 2003, the Space Shuttle Columbia launched on what would be Space Shuttle Columbia's 113th and last flight. About 82 seconds after launch, a big chunk of foam broke off of the external tank. This external tank contained liquid oxygen and liquid hydrogen. They were the fuel that was powering the main engines on the space shuttle. Because that liquid oxygen and liquid hydrogen is at temperatures that are hundreds of degrees below zero, that tank is covered in an insulating foam, and that's that orange foam that you see here. The problem is with the space shuttle is for a number of years they had foam breaking off the external tank. Now, most of the time when that foam broke off, it just missed the space shuttle. Every now and then it would collide with the space shuttle and damage the tiles on the space shuttle. And on STS-107, the 113th flight of the space shuttle program, sorry, it wasn't the 113th flight of Columbia, it was the 113th flight of the space shuttle program and the last flight of Columbia. On STS-107, when that foam broke off and it hit the wing on the space shuttle, it significantly damaged the heat protective tiles that line the front side of the wing on the Space Shuttle Columbia. So a large piece of foam broke off from the external tank. It hit the reinforced carbon-carbon panels on the front wing of the front of the left wing of Columbia, and it severely damaged, if not outright broke, one of those panels. Now, those panels were essential to protecting Columbia from the heat of reentry, and when that panel was damaged and destroyed on launch, when they re-entered on February the 1st, 2003, hot gas from that re-entry was able to get into, and it was able to melt the structures inside the wing. That wing ended up collapsing, and then Columbia burned up on re-entry, and all 7 crew members were killed on re-entry. Now, a question occurred while the space shuttle was in orbit. Video cameras that were photographing the launch saw this piece of foam break off the Space Shuttle Columbia, and they saw it strike the wing. The question was how much damage was done to the wing, and that was not clear. Now, engineers and managers of the Space Shuttle program eventually decided that the piece of foam that broke off and struck the wing probably was not large enough to do significant damage. And of course, they were tragically wrong in that assessment. And there's been a lot of studies as to how they came to that wrong decision, which cost the lives of the 7 crew members. But one of the questions that has come up was, if they had discovered the problem while they were in orbit, was there anything they could do about it? And the answer is they didn't have a repair kit on board. There was nothing they could do on the Space Shuttle Columbia to repair the damage. The question is then, could they have found a way to make their way to the International Space Station, which is also orbiting the Earth? And could they have actually then, because the crew couldn't come home, the Space Shuttle was too severely damaged to come home, could they have changed their orbit to match the orbit of the space station and just hung out on the space station until we could mount a rescue operation to bring them home? After all, the space station, although it's not designed to have that many extra crew members, could certainly support them for a short period of time, and there would be more than enough food and clothing and other things on board to keep them alive for even weeks or a few months while we mounted a rescue operation. So let's calculate how much energy it would have taken to convert the orbit of STS-107 into the orbit that the International Space Station has. And the primary difference between the two orbits is that the Space Shuttle, on that last mission for Columbia, its orbit was inclined at 39 degrees, and for the International Space Station, the orbit was inclined at 51.6 degrees. How much delta V would be required to change from this orbit to that orbit? Well, STS-107 had been launched into a 39-degree inclination orbit. The space station was inclined by 51.6 degrees. That formula that we just saw, the delta V that's required, would be 2 times the circular orbit velocity times the sine of the difference between the angles, 51.6 minus 39 divided by 2. If you plug the numbers into your calculator and work it out, it would require a delta V of 1,700 meters per second. And the problem with a delta V of 1,700 meters per second is that, as we've already seen, the space shuttle only carried a capacity to change its speed by 300 meters per second when it was on orbit. So even if they had discovered, while the space shuttle was on orbit, that the wing was irreparably damaged and there was nothing they could do, the crew did not have enough maneuvering fuel on board to change their orbit to match the orbit of the International Space Station. And by the way, I'm just talking here about the plane change that would be required to go from a 39-degree inclination orbit to a 51-degree inclination orbit. We haven't also accounted for the fact that the two of them were at slightly different orbital altitudes, and we haven't accounted for the fact that the two of them did not have the same right ascension of the ascending node, and that would have required additional fuel as well. So there was no hope of using the thrusters on board the space station to change its orbit to match that of the International Space Station and allow the crew to use that as a safe haven until they could be rescued. All right, so let's go back to changing from a low Earth orbit to a geostationary orbit. We said that you have to do two things. You have to do a plane change so that the orbital inclination that you launched with, for example, if you launch due east out of Florida, as we'll see in the next lecture, you end up in an orbit that's inclined about 28 degrees with respect to the equator. So if you're in this 28-degree orbit and you need to be in a 0-degree orbit, you have to do a plane change, and you have to do a burn up here to circularize your Hohmann orbit. There is a way to save energy to do this, and that's to take advantage of Kepler's second law. What many satellite operators do is they don't put their satellite into an orbit that gets up to geostationary orbit and comes back again. They put it into what's called a super geostationary transfer orbit. This is a transfer orbit that goes way above the geostationary transfer orbit. So it's not a Hohmann orbit because it's not the minimum energy one, but it gets you way, way above the geostationary orbit. And you might wonder, why would you do that? Why would you go way beyond where you want to go? Remember Kepler's second law. The satellite is traveling very, very quickly here. As it climbs up way above geostationary orbit, up here it's moving very, very slowly. And see, the thing about an orbital plane change is it depends on how fast you're moving at that moment in time. If you wait until the satellite is moving really slowly up here and do your orbital plane change then, or in fact, what you have to do is design this orbit so that at some point high above geostationary orbit, you're crossing the 0 degree, you're crossing the Earth's equator. That's when you do your plane change. And the thing is, from the vis viva equation, you're traveling so slow up here that the energy required to do your orbital plane change is significantly less. So you can save a lot of energy on your plane change. Now that you're in this super transfer orbit, though, you still have to fire your engine to get into the geostationary orbit. That's going to require some extra energy, but you save a lot of energy by doing this. So sometimes you will see satellite operators launch their geostationary satellites into orbits that go way above the geostationary orbit. And the reason they're doing that is to take advantage of when they're at apogee up there, when they're traveling really slow. That's the best time to do the plane change. And then you fire your engines again to bring yourself into this geostationary target orbit. So the advantage to this is it requires less delta V, especially if you're launching from a launch site that's at a very high inclination. But the con to this super GTO transfer is that it takes longer to establish the final orbit. So that ends part 3 of lecture 4. Join me in part 4 of lecture 4, where we will finish off lecture 4 and we will talk about orbital rendezvous. Now that we've talked about changing orbits, we will talk about what it takes to get two vehicles to meet and match their orbits in space.